Reality is not what it seems. The solid ground beneath your feet, the passing of time, the sense that the world is made of things, objects, matter, stuff. All of it feels stable, predictable, real. But what if that's just a carefully constructed illusion? For centuries, we believed atoms were the building blocks of everything, tiny solid particles that form all matter in the universe. Your body, your thoughts, this very moment, all built from atoms. But here's the truth. The more closely scientists study atoms, the more the entire idea begins to fall apart. Atoms are not solid. They're not stable. They don't even have a fixed position. They vanish and reappear. They exist in multiple states at once. And, most unsettling of all, they might not exist in any definite way until they're observed. Think about that. Everything you've ever known, touched, or remembered may be constructed from things that aren't fully there until you look at them. So if atoms, the very foundation of everything, don't behave like real physical things, what does that say about the world we live in? Is reality something we create by observing it? Are we shaping the universe simply by being aware of it? Or is everything we think we know just a glitch in the system? This isn't fiction. This is quantum physics. And it might be the strangest, most unsettling truth science has ever uncovered. You've probably heard this 100 times in school. Everything is made of atoms, tiny, solid building blocks, the foundation of all matter. Your body, your phone, the air, the stars, all just combinations of these little particles, right? It's one of those facts we grow up never really questioning. Atoms are the most basic, most certain part of reality. But what if that's not actually true? What if atoms aren't solid? What if they're not even really there the way we think they are? For most of history, we imagined atoms as miniature marbles, simple, indestructible pieces of matter. Then scientists started zooming in, using better tools, smarter experiments, and more powerful math. And what they found didn't match the picture we had in our heads. The atom, it turns out, is mostly empty space. The solid parts we thought we understood, the electrons, the nucleus, started behaving in ways that just didn't make sense. Electrons didn't orbit the nucleus like little planets. Instead, they existed in a blur, a cloud, a region of probability. We couldn't say exactly where they were. And even weirder, when we tried to look at them, to measure them, to pin them down, they changed. Just the act of observing them made them behave differently. It's like reality itself was reacting to us watching. That's not how solid things are supposed to work. And it didn't stop there. Scientists found that these particles could be in multiple states at once, that they could affect each other across impossible distances, that they could disappear and reappear. That time, space, cause and effect, all the stuff we rely on to make sense of the world, breaks down when you get small enough. At the quantum level, the rules just don't apply. So now, we're left with this strange, unsettling idea. Maybe atoms, these supposed building blocks of everything, don't really exist in the way we were taught. Maybe they're not things, but events. Maybe they're not solid objects, but patterns that only become real when we interact with them, when we observe them. Maybe without someone or something watching, atoms don't fully take form at all. It sounds like science fiction, but this is real science. It's tested, observed, and repeated. It's the foundation of quantum mechanics, one of the most successful theories in all of physics. And yet, it throws everything we thought we knew about reality into question. So now we have to ask, if atoms aren't what we think they are, if they're uncertain, unstable, or even dependent on us to exist, then what does that say about the world around us? What does that say about us? Let's try to make sense of the strangest truth in science and explore whether atoms and everything built from them are even real at all. When you look around, everything seems solid, stable, predictable. The wall you lean against pushes back with the same resistance every time. Your phone drops, and it falls, every single time. Cause and effect, the foundation of how we understand the world. But when scientists began investigating the smallest components of reality, atoms, they stumbled upon a shocking truth. Atoms don't follow the rules we've come to expect. They don't behave like solid, predictable objects. Instead, they flicker in and out of existence, vanishing and reappearing in unpredictable ways. It's like a glitch in the very fabric of reality. One moment they're here, the next, they're gone. And it's not just atoms that are strange. The more scientists study the quantum world, the more they realize that everything we thought we knew about matter and reality is a lie. In the quantum realm, particles don't exist in a solid form. They exist in clouds of possibilities. You can't even say where they are until you look. When you observe them, they behave differently. It's like the very foundation of the universe is hiding behind a veil, refusing to show its true nature. So, if atoms can't be trusted to behave like solid objects, what does that mean for everything else we consider real? What if reality itself is just an illusion, held together by our limited understanding? The truth is, we might be living in a world that doesn't exist the way we think it does. And that, right there, is a problem that could change everything. The classic picture of atoms is wrong. For generations, people believed they had a pretty solid understanding of what atoms looked like. The concept was simple, intuitive, and honestly, kind of beautiful. Picture this: a dense, solid nucleus, sitting right at the center, surrounded by tiny electrons gracefully orbiting around it, just like planets spinning around the sun. It made sense. It was easy to visualize. And for a long time, it was the go-to mental image for what atoms were supposed to be. A tiny solar system, neat and orderly, with everything in its place. This model didn't just come out of nowhere. It evolved from a line of thinking that dates back centuries. Philosophers like Democritus had first suggested that everything was made of indivisible particles, atoms, and later scientists started filling in the blanks with observations, experiments, and theory. As scientific tools improved and understanding deepened, atomic models became more refined. The solar system model really took hold in the early 20th century, largely thanks to physicist Niels Bohr. According to Bohr's vision, electrons orbited the nucleus in well-defined paths, or shells, with each orbit representing a specific energy level. It was tidy, it was mathematical, and for many purposes, it even worked. But here's the twist. That mental image we've all grown up with, it's wrong. Not just slightly inaccurate or incomplete, fundamentally wrong. As physicists started probing deeper into the behavior of atoms, especially at extremely small scales, they realized that the solar system analogy falls apart completely. Electrons weren't orbiting in predictable circles. They weren't following set paths. And, weirdest of all, they weren't even there in the way we usually think about things being somewhere. Instead of neat orbits, what scientists saw was more like a fog, a cloud of probabilities. An electron might be here, or there, or somewhere in between. It wasn't fixed. It wasn't certain. It was fuzzy. This fuzziness is where quantum physics really begins to show its face. To understand just how strange this gets, imagine trying to photograph an electron. You set up a super tiny camera, press the shutter, and in that split second, the electron is in one spot. But if you try again, it might appear somewhere else. Try a third time, and it's moved again. Over many, many snapshots, a pattern starts to form. Not of an object following a predictable route, but of a probability distribution. It's like the electron is smeared out across space, only coalescing into a definite location when we measure it. In other words, it's not that the electron is hiding, and we just haven't found it yet. It's that the electron genuinely doesn't have a precise location until we look. This idea shattered the classical understanding of physics. For centuries, science had relied on the assumption that objects exist independently of observation. A rock is a rock, whether you're looking at it or not. A planet continues its orbit around the sun, whether you're watching through a telescope or sleeping in your bed. But on the quantum scale, this assumption simply doesn't hold. Particles behave differently when they're being observed, not just in some metaphorical sense, but in a measurable, repeatable way. One of the most famous demonstrations of this is the double-slit experiment. When electrons are fired one at a time at a screen through two narrow slits, they produce an interference pattern, as if each electron is behaving like a wave, passing through both slits at once and interfering with itself. But as soon as you try to observe which slit the electron goes through, the interference pattern disappears. Now, the electrons act like little particles, choosing one slit or the other, no longer interfering like waves. The mere act of measuring collapses the possibilities into a single outcome. It's as if nature waits to see whether you're watching before deciding how to behave. This phenomenon is known as wave-particle duality, and it's one of the strangest, most mind-bending aspects of quantum mechanics. It tells us that particles like electrons are not just particles, they're also waves. But they're not really waves either, at least not in the traditional sense. They exist in a superposition, a blend of all possible states, until something forces them to pick just one. And that something is often the act of observation. So when we ask, where is the electron? The quantum answer is, nowhere in particular, and everywhere it could possibly be. Until we check. Until we measure, the electron lives in a state of potential. It's a mathematical wave of probabilities. It only snaps into a specific location when we interact with it. Before that, it's more like a ghost. This forces us to rethink what it means for something to exist. In our everyday world, existence feels obvious. You're either in a room or you're not. A car is either parked on the street or it isn't. But in the quantum realm, existence is less about being in one place and more about the potential to be in many places. And that's a hard concept to wrap your head around. Even stranger is how this behavior scales with complexity. At the atomic level, particles regularly inhabit multiple states at once, interfere with themselves, and only settle down when observed. But what happens when you have more than just one particle? What about 2, or 100, or 1 billion? As it turns out, things get even weirder. When particles interact, they can become entangled, forming a deep connection that links their states no matter how far apart they are. Measure one, and the other instantly knows, even if it's on the other side of the universe. This instant communication doesn't transmit information in the traditional sense, so it doesn't break the speed of light, but it shows us just how interconnected the quantum world is. It's like the universe itself is a web of probabilities and potentialities, woven together in ways we're only beginning to understand. And all of this, the fuzziness, the probabilistic nature of particles, the collapse of the wave function when observed, shows just how far we've come from that original, innocent picture of atoms as miniature solar systems. That model, as neat and elegant as it was, simply can't handle the bizarre, counterintuitive behavior of the quantum world. Electrons are not tiny planets. They don't orbit in neat circles. They don't even have a clear position until forced to. They're ghosts of possibility, dancing in a blur until we dare to peek. This isn't just some abstract philosophical idea either. It has real, measurable consequences. Quantum mechanics underpins modern technology, semiconductors, lasers, MRI machines, and quantum computers, to name a few. Every time you use your phone, you're relying on the quantum rules that govern how electrons move through materials. So even if this stuff sounds like sci-fi, it's already deeply embedded in your everyday life. The classic picture of atoms gave us a starting point, a mental model to work from. But the universe, it turns out, is far stranger, subtler, and more mysterious than anyone ever imagined. And the closer we look, the less solid, less certain, and less real the building blocks of matter become. We no longer live in a clockwork universe where everything ticks along predictably. We live in a world built on uncertainty, probability, and the unsettling truth that reality itself doesn't fully exist until we look. Observation changes reality. Imagine setting up a simple experiment. You place a tiny particle, say an electron, in front of a barrier with two narrow slits, and behind that barrier, you set up a screen to detect where the particle lands. Now, if this were an ordinary, everyday object, like a pebble or a marble, you'd expect it to go through one slit or the other and hit the screen directly behind that slit. It's basic intuition, right? That's how we've always seen things work in the macroscopic world. But particles in the quantum world don't follow our intuition. When you fire a single electron at the slits, and then another, something incredibly strange begins to happen. Over time, as you let more and more electrons pass through the slits, a pattern emerges on the screen that looks nothing like two piles of marbles. Instead, you see a series of light and dark bands, an interference pattern, the very same pattern you'd expect if you'd been firing waves at the slits instead of particles. Waves? Yes, like ripples in water. When water waves pass through two slits, they spread out and overlap on the other side, creating areas where the waves reinforce each other, bright bands, and areas where they cancel each other out, dark bands. That's the interference pattern. But here's the wild part. Each electron was fired one at a time. They weren't colliding with each other. They were arriving at the slits independently. Still, somehow, each single electron contributed to that interference pattern, as though it was behaving like a wave, going through both slits at once, interfering with itself. This defies logic. How can a single particle go through two slits at once? How can it behave like a wave, interfere with itself, and then land on the screen as a single dot, like a particle again? The only explanation is that the electron is not just a particle. It behaves like a wave of probabilities, a kind of fuzzy cloud of possibilities that exists in multiple places at once. This idea is captured in what physicists call the wave function, a mathematical description of all the possible places the particle might be found. Until you look, the particle exists in a superposition of all possibilities. It's not here or there. It's here and there. It's in both slits at once. The universe, it seems, is not made of solid, definite things. It's made of probabilities, potentialities, and waves of uncertainty. Now you might think, fine, that's weird, but maybe we just don't know which slit the particle went through. Maybe it still went through one or the other, and we just don't have the information yet. That would be a reasonable assumption if quantum mechanics followed classical rules, but it doesn't. So physicists tried to test this idea. They set up the same double-slit experiment, but this time they added a tiny detector in front of the slits to see which one the particle actually passed through. After all, it has to go through one, right? Here's where it gets even more bizarre. The moment you add a detector to measure which slit the particle goes through, the interference pattern disappears. Just like that. Instead of a series of bands, you get two clumps, like you would with regular marbles. The wave-like behavior is gone. The particle no longer behaves like it went through both slits. It clearly picks one path, one slit, and follows it like a tiny bullet. It's as if the very act of watching the particle forces it to make a decision. It can no longer explore all possibilities. It collapses into a definite state, a single outcome. This isn't just a case of disrupting the particle with your measuring device. Physicists have gone to great lengths to make sure the detectors don't interfere with the particle's motion in any physical way. And yet, even with the gentlest, most careful observation, the same thing happens. Once you try to know which slit it goes through, the wave function collapses. The particle stops behaving like a wave and starts behaving like a particle. It chooses a path. It obeys your expectations. The act of observation changes reality itself. This is not just a fluke of electrons. The same thing has been tested with photons, particles of light, and even with larger particles like molecules composed of hundreds of atoms. The interference pattern remains until you observe. Once you do, it collapses. This forces us to confront a staggering idea. The physical world doesn't fully exist in a definite state until it is measured. Reality isn't just out there, unfolding on its own, independent of us. It is, at least in part, shaped by our knowledge of it. The universe waits to see if we're paying attention before it decides what it wants to be. That sounds ridiculous, magical even, but the mathematics of quantum mechanics supports it. In fact, quantum theory requires this behavior. The wave function evolves smoothly and predictably, describing all the possible outcomes until a measurement occurs. At that moment, the wave function collapses, and one single outcome is chosen. But no one can say why this collapse happens. It just does, and only when someone is watching. Even more mind-bending is the fact that the collapse seems to happen because of observation, not because of light bouncing off the particle, or because of energy being transferred, just the act of measurement, of knowing. And the definition of observer in quantum mechanics isn't limited to human beings. It could be any interaction that extracts information about the system. But when you trace things far enough, consciousness always seems to be lurking in the background, whispering questions we still can't answer. Is reality fundamentally linked to awareness? Does the universe exist in a fuzzy, indefinite state until someone looks at it? Einstein famously hated this idea. He believed the universe existed independently of whether we were looking or not. He said, "I like to think the moon is there, even if I am not looking at it." But quantum mechanics doesn't seem to agree. The famous physicist John Wheeler once asked a deeper question: does the universe require observers to exist? He proposed a thought experiment called the delayed choice experiment, where you could choose to observe or not observe the particle after it had already passed through the slits. The astonishing result? Your decision about whether to observe it after the fact still affected whether it acted like a wave or a particle. It's as if the particle's past behavior depended on your future choice. This messes with everything we thought we knew about time, causality, and reality itself. How can your observation in the present affect the past? Is the past not fixed until it's observed? Are particles somehow aware of our intentions? Or is the universe simply a vast network of possibilities, waiting for consciousness to carve a path through it? Some physicists tried to avoid these uncomfortable conclusions by proposing hidden variables, unknown factors that determine outcomes behind the scenes. But experiments have shown that if hidden variables exist, they would have to be non-local, meaning they'd communicate instantaneously across any distance, faster than the speed of light. This seems to violate relativity, and yet it's what the experiments suggest. So either particles really are connected across space in some spooky, faster-than-light way, or we have to accept that observation is fundamental to reality. No interpretation of quantum mechanics has been able to completely escape the weirdness. Some physicists favor the many worlds interpretation, where all possible outcomes happen, but in parallel universes. The electron went through both slits, but in different branches of reality. In one universe, it chose the left, in another, the right. But you, the observer, only experience one version. It's an elegant solution mathematically, but it doesn't solve the mystery. It just shifts it somewhere else. At the end of the day, we are left with a haunting truth. The very act of measurement, of observation, has a fundamental role in shaping what reality becomes. The quantum world doesn't offer us a clean, deterministic path like Newton's clockwork universe. It gives us something far stranger, an unpredictable, shimmering sea of possibilities, collapsing into certainty only when we peek behind the curtain. And perhaps that's the real lesson here. That reality isn't a static thing. It's dynamic. It's alive with potential. And we're not just passive observers. We're participants. We don't just witness the universe. We help shape it, just by looking. Superposition, being everywhere and nowhere. Let's dive into one of the strangest, most mind-bending ideas in all of quantum physics: the concept of superposition. Now don't let the word intimidate you. This idea is as weird as it sounds, and it flips everything we think we know about reality upside down. At its core, superposition tells us that particles, the tiniest building blocks of everything, don't settle for just one state, one place, or one identity. Instead, they exist in all possible states at once. Yes, you heard that right. Until we measure them, observe them, or interact with them in some way, they are quite literally in all states simultaneously. Imagine flipping a coin. In the everyday world we live in, that coin is either heads or tails the moment it lands. You might not know the result until you look, but the outcome was decided the instant it hit the table. In the quantum world, though, things don't work that way. If a quantum particle were a coin, it wouldn't be heads or tails. It would be both at the same time, until someone peaked. Only then would it choose a side. Before that, it's like it's suspended in a cloud of possibilities. This is not just speculation. This isn't some abstract metaphor cooked up by physicists to sound cool. This is a measurable, observable, repeatable phenomenon that's been tested in labs around the world, and it has stood the test of time for over a century. It's as real as gravity, as real as electricity. But it's so weird, so deeply counterintuitive, that even the brightest minds in science have struggled to wrap their heads around it. To make sense of this, we can thank one of the most famous thought experiments in all of science, Schrödinger's cat. You've probably heard of it, and maybe even joked about it. But this seemingly simple scenario hides one of the most unsettling truths about the quantum world. Picture this. You place a cat inside a sealed box. Inside the box, there's a tiny bit of radioactive material, just a single atom. Now, quantum mechanics tells us that this atom might decay, or it might not. And here's the twist. Until we observe it, it exists in a state of superposition, where it has both decayed and not decayed at the same time. The atom is both things at once. This atom is connected to a device that will break a vial of poison if the atom decays. So, if it decays, the poison is released, and the cat dies. If it doesn't decay, the poison stays sealed, and the cat lives. Pretty straightforward, right? But here's the problem. Because the atom is in a superposition of decayed and not decayed, the poison is in a superposition of released and not released, and the cat, incredibly, is in a superposition of alive and dead. That's the nightmare of Schrödinger's cat. Until you open the box, the cat is not just hidden from your view. It literally exists in both states, alive and dead, at the same time. It's not that we don't know whether the cat is alive or dead. It's that the cat itself doesn't decide until someone looks. This thought experiment was never meant to be taken literally. Schrödinger actually came up with it to show how absurd quantum mechanics seemed when applied to everyday objects. But here's the kicker. The math says it's real. The equations don't blink. And when scientists actually test the underlying principles with real particles, electrons, photons, atoms, they behave exactly like the cat in the box. They exist in multiple states at once, and when we observe them, they suddenly snap into one clear state. It's like reality doesn't commit to a story until someone is watching. This idea flies in the face of classical physics, where everything is neat, deterministic, and predictable. In the world of Newton and Einstein, objects have clear positions and velocities. There's no ambiguity. But quantum mechanics plays by a different set of rules. Particles don't have definite positions until we look. They don't have definite paths until we force them to choose. It's like the universe is constantly branching into different possibilities, and only when we step in and observe does it collapse into a single outcome. Now let's be clear. This isn't just weird science for the sake of being weird. Superposition is more than a thought experiment. It's something physicists have actually seen, not with cats, but with particles of light and matter. In experiments, photons have been fired through slits and observed interfering with themselves. as if each photon went through both slits at once, not chose one, not bounced back and forth, but literally traveled both paths until a detector forced it to choose. When no one looks, the photon behaves like a wave, exploring all possibilities. But the moment you set up a detector to check which path it took, the wave collapses, and it acts like a particle. One path, one outcome, one reality. What's even crazier is that this effect scales up, not just to individual particles, but to molecules, and potentially even larger systems. Researchers have already demonstrated superposition with molecules made of dozens of atoms, and there's no theoretical limit to how big this can go. In principle, even a baseball could be in a superposition. We just don't see it, because as objects get bigger, they interact more with their surroundings, and these interactions force them to choose a state. That's why you never see a blurry, ghost-like baseball. But the math says it's still possible. This is where quantum mechanics gets philosophical, not because it wants to be, but because it has to be. If observation causes reality to snap into place, then what does that say about reality itself? Is the universe just a soup of probabilities until someone observes it? Are we creating reality by looking at it? And who, or what, is the ultimate observer? For decades, physicists have debated these questions. Some say that observation doesn't need a conscious mind, that any interaction, even with a measuring device, is enough to collapse the wave function. Others argue that consciousness does play a special role, that reality doesn't become real until a mind observes it. And still others go even further, proposing that every possible outcome happens in a vast multiverse. An observation just determines which version of reality you land in. Whichever interpretation you prefer, one thing is clear: superposition is not just a quirk, it's a fundamental feature of how the universe works. It's not just some theoretical footnote tucked away in a physics textbook. It's something we can observe, measure, and even harness. Quantum computers, for example, rely entirely on superposition. Traditional computers store data in bits, zeros and ones, but quantum computers use qubits, which can be 0, 1, or both at the same time, thanks to superposition. This allows quantum machines to perform calculations in ways that regular computers never could. They're not just faster, they're a whole different kind of intelligence, capable of solving problems that would take classical computers longer than the age of the universe. So while the idea of a cat that's both alive and dead might sound like pure science fiction, it's actually at the heart of some of the most cutting-edge science happening today. Superposition isn't just real, it's practical. It's powering the next revolution in technology. It's changing how we understand information, computation, and the very nature of existence. And maybe, just maybe, it's telling us something even deeper, that the universe is stranger, richer, and more mysterious than we ever imagined. That reality is not a solid, fixed stage where events unfold, but a shimmering field of possibilities, waiting to be observed, waiting to be chosen, waiting to become real. In the end, superposition reminds us that the universe doesn't just exist out there, independently of us. In some eerie, fundamental way, we're part of the equation. We're not just observers, we're participants in the cosmic dance, and every time we look, we help shape the music. So, are atoms even real? It's a strange question, right? On the surface, it feels almost silly. After all, we learned from a young age that atoms are the basic building blocks of matter. Everything, your body, your phone, the air, the stars, is made of atoms. They're the little Lego bricks of the universe, tiny, solid, indivisible units of stuff that clump together to form bigger things. That's how the story goes. But quantum physics doesn't care much about stories we like. And the more we zoom in, the more that neat little picture falls apart. When scientists began probing atoms more closely, expecting to find some solid essence at their core, they found nothing. Not nothing, as in, we just don't know yet, but nothing as in, what we thought was solid isn't. The atom is almost entirely empty space. And the parts that aren't empty, even they don't behave the way we'd expect physical things to behave. Electrons, for example, don't spin around the nucleus in tiny orbits like planets around a sun. That's just a metaphor we invented to make sense of them. In reality, they exist in a kind of cloud, a probability field, a haze of maybes. Try to imagine this. An electron isn't at a specific place until you look for it. Until then, it's smeared out, like a wave of possibilities. It could be here, or way over there, all at once. But the moment you measure it, it chooses a location. Why? We don't know. All we know is that the very act of observing, of trying to find where the particle is, forces it to be somewhere. Before that, its position is undefined, not hidden, not unknown, just not there in the way we usually think of things being there. And this doesn't just apply to electrons. The same uncertainty applies to all particles, even entire atoms, even groups of atoms, even molecules. Everything made of matter exists in this shimmering limbo of probability until you observe it. That observation collapses the possibilities into one outcome. It's called the collapse of the wave function, and it's one of the most bizarre aspects of quantum mechanics. But let's take a step back and think about what this really means. If atoms don't have definite positions, if they flicker in and out of potential states, existing as mere likelihoods until observed, then what does that say about the world around you? Your chair, your desk, your brain, your body. If all of those are made of atoms, and atoms don't settle down into a defined state until they're interacted with, is anything really there when no one's looking? It's almost as if the universe is running some kind of simulation, rendering only what's being watched, like a video game that saves processing power by only loading the part of the world your character can see. The rest? It's just code, waiting to be activated, waiting for an interaction, a player, an observer. And no, this isn't just poetic philosophy or science fiction. These are real implications of quantum physics, backed up by mountains of experimental data. The famous double-slit experiment, for example, showed that particles behave like waves when unobserved, but act like particles the moment they're measured. It's not a metaphor. It's an observable, repeatable result that defies classical logic. Reality changes based on whether or not you're watching. Einstein hated this idea. He couldn't accept it. To him, the universe was objective, solid, out there doing its thing, regardless of who was looking. He once said, "I like to think the moon is there, even if I'm not looking at it." And who could blame him? It's a comforting idea. But quantum mechanics doesn't care about comfort. It doesn't offer a cozy, reliable universe that exists independent of us. Instead, it offers something far more slippery, a universe that seems to need an observer to come into sharp focus. So, again, are atoms real? Well, they're real enough to make things work. We build electronics based on quantum physics. We use it to power lasers, MRI machines, and GPS systems. It's not just theory, it works. But the kind of real we're talking about here isn't the old school kind. It's not tiny solid balls bouncing around in space. It's not stuff you can point at and say, there it is. It's more like a shifting web of potentialities, a network of probabilities that responds to interaction, to consciousness, to choice. Think of atoms not as little marbles, but as questions waiting for answers. Until you ask the question, where is this particle? What's its position? What's its speed? You don't get a concrete answer. And when you do ask, the universe gives you one answer, at the cost of erasing all the others. The rest of the possibilities vanish, as if they were never there. But they were there, at least mathematically. In some sense, they were part of reality, until they weren't. This has led some physicists and philosophers to wonder whether reality itself is fundamentally informational. Maybe what we experience as the physical world is just a kind of output, a result that emerges from deeper rules. rules that are more abstract. Maybe space, time, and matter are just the tip of the iceberg, and beneath them lies a world made not of things, but of relationships, measurements, interactions. And here's the weird part. There's no experiment we've ever done that breaks this rule. Every time we look, the quantum world plays by these strange rules. No matter how much we want a normal answer, we get the quantum one. This is how atoms behave. This is what they are. Or, more precisely, this is what they do. Because the closer we look, the less sense it makes to talk about what an atom is. It only makes sense to talk about what it does when you interact with it. So maybe we've been asking the wrong question all along. Maybe, are atoms real? Isn't the question we should be asking. Maybe the better question is, what is reality if it only crystallizes when observed? And then, what does that say about us? Because if the universe requires observation to snap into place, then the observer, you, me, us, suddenly becomes very important. Maybe consciousness isn't just a passive witness to reality. Maybe it plays a role in bringing reality into being. That idea used to be fringe, but now it's being seriously considered in some interpretations of quantum mechanics. Does that mean the universe only exists because we're here to see it? Not necessarily, but it does mean that reality and observation are deeply intertwined. They're not separate, they're entangled. In fact, entanglement is a whole other mind-bending quantum phenomenon, where particles can be linked across space and time, instantly affecting one another no matter the distance. Einstein called it spooky action at a distance, and it's real. It's been tested and confirmed over and over. So here we are, made of atoms, living in a world made of atoms. And yet, the more we understand about them, the less solid everything seems. The universe begins to look less like a machine and more like a dance, a system of interactions, a symphony that only plays when the audience is present. Maybe we've never truly touched the physical world. Maybe there's nothing solid to touch in the first place, just layers of probabilities collapsing into moments, just a series of outcomes triggered by awareness. Maybe we're not walking through a physical world, but surfing the wave of its possibilities. So, are atoms real? They're as real as anything else in this strange, shifting cosmos. But if you're picturing tiny little balls building up the universe like blocks, it might be time to rethink that image. The truth, as always in quantum physics, is far stranger than fiction. Entanglement. Spooky connections across space. Quantum entanglement might just be one of the most mysterious, mind-bending phenomena in all of physics. It's the kind of concept that sounds like it belongs in a science fiction novel, not a real-world laboratory, but it is real, verified, tested, and observed. And yet it still defies our most basic intuitions about space, time, and how the universe should work. So, what is quantum entanglement? Imagine two tiny particles, electrons for example. Under certain conditions, these particles can become entangled, meaning their properties become deeply linked, no matter how far apart they are in space. It's as if the particles are no longer two separate objects, but one single system that exists in two places at once. When you measure something about one particle, say, its spin, the other particle's spin is instantly determined. Not after a signal travels between them. Instantly. This isn't just weird, it's universe-breaking. Albert Einstein absolutely hated this idea. He famously referred to it as spooky action at a distance, and it's not hard to see why. In Einstein's world, nothing, no information, no influence, no interaction, can travel faster than the speed of light. That's the ultimate speed limit of the cosmos. If you wanted to send a signal from one side of the galaxy to the other, it would take tens of thousands of years, even at light speed. But entangled particles, they don't seem to care about distance or speed. They react to each other instantly, as if space and time aren't even a factor. Let's go a little deeper. At the quantum level, particles don't have fixed properties until we observe them. This is already strange. A particle doesn't have a specific position, momentum, or spin until we look at it. Instead, it exists in a kind of blur, a cloud of probabilities. But when two particles become entangled, their probabilities become intertwined. If you observe one particle and it ends up spinning up, the other particle must spin down, even if it's light years away. You don't even need to look at the second particle. The moment you measure the first one, the outcome for the second is set in stone. It's not that one particle is sending a message to the other, telling it what to do. That would still require time. What's more mind-blowing is that there seems to be no message at all, just an instantaneous shift across space. Einstein wasn't convinced. He thought that maybe these particles were secretly carrying some hidden information, some pre-programmed instruction set that told them what results to give when measured. This idea is known as local hidden variables. Basically, Einstein was saying, the particles aren't talking to each other. They just already knew what they were supposed to do from the beginning. This was a comforting idea because it kept the universe logical, local, predictable. It meant that physics wasn't as weird as quantum mechanics made it seem. But as elegant as the idea was, it had a problem. No one could find any evidence for these hidden variables. Then came John Bell, a physicist who in the 1960s proposed a brilliant way to test whether local hidden variables actually exist. He formulated what's now called Bell's theorem. Without diving too deep into the math, Bell showed that if hidden variables were real, then certain statistical patterns should show up when entangled particles are measured. But if quantum mechanics was right, if entanglement really worked the way it claimed, then different patterns would appear. And so, the experiments began. Over the years, physicists set up increasingly sophisticated tests of Bell's theorem. They created pairs of entangled particles and sent them in opposite directions. They measured their properties using randomized settings, carefully avoiding any possible signal that could travel between them. Again and again, the results confirmed what quantum mechanics predicted and ruled out the idea of hidden variables. In fact, the latest experiments have closed nearly every loophole. Entanglement is real, and it really does involve instant correlations that defy our classical understanding of space and time. But how can this be? How can two objects, separated by vast distances, be so deeply connected? Some physicists believe the answer lies in a more radical idea, that space itself is not fundamental. In other words, space, the thing we move through, the thing we measure distances with, might not be the true underlying fabric of the universe. It might just be an emergent property, something that arises out of more basic, invisible connections. Think of space as a kind of illusion, a stage set that only appears solid and continuous. But behind the scenes, the actors, particles, are connected through threads we can't directly see. In this view, entanglement isn't some mysterious force jumping across space. It's a clue that space might not be what we think it is. That may be, at the most fundamental level, everything in the universe is connected, not by signals or waves or forces, but by pure information. And entangled particles are simply revealing this hidden, non-local web. This idea isn't just philosophical. It's starting to shape how physicists think about black holes, the nature of gravity, and even the origins of the universe itself. Some theories suggest that space, time, and gravity might all emerge from a deeper layer of reality made entirely of quantum entanglement, that the geometry of space-time could actually be a manifestation of entangled information. Let that sink in. If that's true, then what we perceive as distance, the separation between you and me, between Earth and a distant star, might not be fundamental at all. The universe could be stitched together not by space, but by relationships. And when we see two particles behave as one across light years, we're not seeing a signal being sent. We're seeing a deep unity that was always there, a unity that our current understanding of physics is only beginning to uncover. Now, to be clear, Entanglement can't be used to send messages faster than light. That's the catch. You can't control what result you get when you measure an entangled particle. So while the other particle is instantly affected, you can't use that to transmit information. It's like flipping two coins that always land on opposite sides, but you don't get to choose heads or tails. So even though entanglement is faster than light in a sense, it doesn't violate relativity in a way that allows for time travel or faster than light communication. But still, the fact that this even happens at all is extraordinary. Think about it. Every time we test entanglement in a lab, we're not just doing a cool physics trick. We're reaching into the heart of the universe and tugging on a thread that stretches across reality. We're watching two distant pieces of the cosmos behave like one. We're witnessing the breakdown of the very ideas of separation, distance, and independence. It challenges the way we think about the world. We're so used to thinking in terms of location, proximity, and cause and effect. But quantum entanglement throws all of that into question. It tells us that the universe is weirder, more connected, and more unified than our senses can perceive. And here's the kicker. This isn't just theory. This isn't just math on a blackboard. Entanglement has been demonstrated in countless experiments, and it's now being used in real-world technology. Quantum computers, quantum cryptography, and quantum networks, all of them rely on entanglement to work. The spooky action Einstein despised is now at the core of a technological revolution. So next time you look up at the stars and wonder how far they really are, consider this. Distance might not mean what you think it does. In the quantum world, separation is an illusion, and entanglement is the thread that pulls everything together, revealing a universe far stranger and far more connected than we ever imagined. Reality is a question, not an answer. The deeper scientists dig into the quantum realm, the stranger things get. It's like peeling back the layers of what we think is real, only to find out that reality itself might be more like smoke than stone, shifting, uncertain, and dependent on something we don't fully understand. And the more we learn, the clearer it becomes. Reality isn't as fixed or solid as we once believed. It's more like a question begging to be asked than an answer we've already found. You see, in our everyday lives, we take a lot for granted. We assume objects exist, whether we're looking at them or not. We think time flows steadily, ticking away in perfect order from past to future. We believe things are where they are, doing what they do, regardless of whether anyone's paying attention. But quantum mechanics throws all of that out the window. At the quantum level, matter doesn't behave like matter. Particles don't act like tiny marbles bouncing around in predictable paths. Instead, they blur into waves of possibility. A single particle can be in many places at once, in many states at the same time, until something or someone comes along to measure it. This is what we call a superposition. It's not just a weird mathematical trick. It's a real phenomenon that has been tested over and over again. And every time it forces us to ask, what is this particle doing before we look at it? Is it anywhere? Is it everywhere? Is it even real before we observe it? It gets stranger, because the act of observing doesn't just tell us what's happening, it actually seems to change what's happening. Imagine that. Reality might not fully form until it's being watched. This idea is at the heart of what's called the observer effect. It's not that a scientist sitting in a lab is bending the universe to their will with a glance. It's that, in a deep and subtle way, the universe seems to wait for attention. Until then, it holds its cards close, hiding behind probabilities and potential outcomes. Let's take the famous double-slit experiment. It's simple in design, but the implications are enormous. When you shoot particles, say electrons, through two slits without measuring them, they behave like waves. They create an interference pattern as if each electron is going through both slits at once, interfering with itself. But the moment you observe which slit the electron actually passes through, the interference pattern disappears. Suddenly the electrons behave like particles again, choosing a definite path as if they knew they were being watched. It's as if the universe was undecided until someone came along and asked it to make a choice. And what's even more astonishing, this effect doesn't just apply in tiny, insignificant labs. It applies across the universe. Light from distant galaxies, billions of years old, can also exhibit these effects. So the implications are not just local, they're cosmic. If observation collapses possibilities into a single outcome, then is reality only real when something is there to witness it? This brings us to a provocative thought. Maybe reality is participatory. Maybe the world we see around us isn't an objective stage that exists on its own, but a kind of unfolding story that only takes shape when it's being read. Maybe the moon really isn't there unless someone looks at it, or at least it isn't there in a definite way. It's not just poetic, it's quantum, and it's a nightmare for anyone who wants a nice, clean, clockwork universe. For centuries, physicists believed that if you knew all the forces at play and all the positions of all the particles, you could predict the future with perfect accuracy. But quantum mechanics shattered that dream. At its core lies uncertainty, not because we lack the tools or knowledge to see the full picture, but because the full picture doesn't exist until it's viewed. This makes us ask, what is the role of the observer? Is the observer just another part of the system, or something more fundamental? Could consciousness itself be tied to the very structure of reality? Some interpretations, like the Copenhagen interpretation, suggest that the act of measurement collapses the wave function, turning probability into a fact, but it never really says how or why. Other interpretations go even further. The many worlds theory, for example, says that every possible outcome does happen, but in different universes. When you observe an event, you're not collapsing anything. You're simply stepping into one of many branching realities. But still, the question lingers. What makes this version real to you? Why are you experiencing this outcome and not another? That brings us to the heart of the mystery. Reality doesn't behave like a cold, objective machine. It behaves more like a fluid canvas, shaped, at least in part, by interaction, by observation, by awareness. This doesn't mean that we're hallucinating the universe into being. It means the universe might be less of a pre-written book and more of a choose-your-own-adventure, with the reader, you, helping to determine how the story unfolds. So where does that leave us? Maybe we need to rethink what we mean by real. If reality isn't fixed until it's observed, then what is it before observation? Is it a cloud of probabilities, a mathematical abstraction, a potential waiting to be born? And if so, then what does that make us? These observers who bring the universe into focus. Are we participants in a grand cosmic experiment? Are we co-creators of what we call existence? Or are we simply along for the ride, forever chasing a reality that only reveals itself in glimpses, just out of reach? The truth is that quantum mechanics doesn't give us easy answers. It gives us paradoxes, puzzles, and possibilities. It strips away the comforting illusion of certainty and replaces it with something far more dynamic, a universe that is responsive, unpredictable, and deeply intertwined with the act of observation itself. In this way, quantum physics doesn't just challenge our understanding of particles or atoms, it challenges our understanding of ourselves. It forces us to confront the possibility that we are not separate from the fabric of reality, but woven into it. That by observing, we shape. By questioning, we create. By existing, we bring existence into being. So maybe, just maybe, reality isn't something we find. Maybe it's something we ask, something that answers us, not with facts, but with experiences, not with absolutes, but with possibilities, not with a final truth, but with an invitation to explore, to wonder, and to keep asking the question, what is real? Because in the quantum world, the only thing more mysterious than the universe is the part of it that's asking the question, the role of consciousness. Here's where things start to blur the line between science and something that feels almost philosophical. Up until now, we've talked about particles behaving like waves, collapsing into definite states only when observed, and a universe that seems to play by rules that are anything but intuitive. But let's dig deeper, because the next idea takes all of this and points the finger right at you, at your mind, your awareness, your consciousness. Some interpretations of quantum mechanics suggest something pretty wild, that it's not just observation in the passive sense that causes a particle to decide on a state. It's not just light bouncing off an object or a sensor recording data. It's not a machine ticking over. It might be you, the conscious observer, that triggers the change. That the act of being aware of something somehow plays a fundamental role in shaping what that something even is. Let that sink in for a second. In the famous double-slit experiment, a single particle is sent toward a barrier with two slits. If left unmeasured, it acts like a wave, going through both slits simultaneously, interfering with itself, and creating a pattern on the detector screen that looks like what you'd expect from a wave. But if you try to measure which slit the particle goes through, if you try to catch it in the act, it suddenly behaves like a particle. The interference pattern disappears. The wave function collapses. The particle picks a path, one or the other, not both, not some blurry mix of possibilities, a single, definite outcome. Why does this happen? Why should the mere act of measurement cause a shift so dramatic in the behavior of something so tiny? Some physicists, especially those who subscribe to interpretations like the consciousness causes collapse theory, argue that the presence of a conscious observer, someone who can know or be aware of the outcome, might be the critical ingredient. Not the device taking measurements, not the camera recording it, not even a computer analyzing it, but consciousness itself, awareness, that strange, ineffable quality that you experience every moment of your life, but can never quite point to or hold in your hand. If this is true, even partially true, it raises mind-bending questions about the nature of reality. Are things only real when we observe them? Does the moon exist when no one is looking at it? Does the universe need consciousness to exist at all? Are we, in some unfathomable way, co-creators of the cosmos, simply by being conscious within it? Now, to be absolutely clear, this is still very much a topic of debate. Not all physicists agree with this idea, far from it. In fact, many find it deeply uncomfortable, even bordering on pseudoscience. Others argue that it's not awareness that matters, but simply interaction. In their view, the moment a particle interacts with anything else, an air molecule, a photon, a piece of the environment, that's enough to count as an observation. This is the basis of the decoherence approach, the idea that entanglement with the environment is what causes quantum systems to collapse into classical states. In other words, it's not that a conscious mind is needed. It's that the universe is constantly observing itself, and we're just part of that larger system. Still, the fact that this debate even exists at all says something remarkable, because whether or not consciousness is required for wave function collapse, quantum mechanics forces us to reckon with a simple truth. Reality, as we perceive it, is deeply tied to our minds. And our minds, our thoughts, memories, emotions, are built on brains made of neurons, made of molecules, made of atoms, made of subatomic particles, that, according to quantum physics, don't even exist in a definite state unless observed. So what does that mean? What does it mean if the very matter your brain is made of doesn't have clear properties until some kind of observation occurs? What does it mean if, at the most fundamental level, your sense of identity, yourself, is built on something that flickers in and out of probabilistic clouds of possibility? It's unsettling, fascinating, confusing, and somehow intimate. Quantum mechanics tells us that the world is not what it seems, that solidity is an illusion, that particles don't have fixed positions, that time doesn't tick by in a neat, predictable line. And right in the middle of all this strangeness is the observer, you, not standing outside the universe, looking in, but existing within it, made of it, entangled with it, shaping it just by being aware. Some philosophers and scientists have even speculated that consciousness might be a fundamental feature of the universe, not an emergent property of complex biology. This is the idea behind panpsychism, the notion that awareness exists at some level in all things. Or, if not awareness as we know it, then at least a proto-consciousness, a kind of raw experience or capacity for perception embedded in the fabric of reality itself. It sounds like science fiction, but then again, so did quantum mechanics before it was tested. Let's say for a moment that this consciousness plays a role idea is correct. That observation by a conscious being is necessary for the universe to choose a state. Then it opens up even stranger ideas. What about when no one is looking? What about the early universe, before life existed? Was everything in a state of superposition? Did the universe need to wait for consciousness to emerge in order for anything to be real? Or, if you take the other view, that consciousness isn't required at all, you still end up in a place where the role of the observer matters. Even if it's just a photon bouncing off a particle, it's the interaction that defines reality. There is no such thing as a perfectly isolated system. Everything is tangled up with everything else. Everything is influencing everything else. Reality isn't just a thing that is. It's a process that's always happening, always unfolding. And somehow, you're part of that process. You, with your thoughts and dreams and questions. You, who looks up at the stars and wonders what it all means. You, who is made of atoms that don't know where they are or what they are until they are seen. You are not just in the universe. You are the universe, observing itself, becoming aware of itself. So when you think about your mind, your consciousness, your sense of self, it's not separate from the laws of physics. It's not an afterthought. It's not an illusion. It's something that's deeply tied into the most mysterious aspects of reality that we know. Maybe one day we'll understand it better. Maybe we'll unlock the quantum nature of consciousness the same way we unlock the atom. Or maybe it'll always remain a mystery, right at the edge of what we can comprehend. But either way, the next time you ask yourself, "Who am I?" remember, that question might be more profound than we ever imagined, because the answer might not be found just in biology or psychology or philosophy, but in quantum physics itself, and that changes everything. So, what's actually real? At this point, you might find yourself staring into the void of all this information, wondering if atoms aren't solid, if time doesn't tick like a clock, if particles don't even exist in definite states until something observes them, and if even the observer might influence reality, then what's real? Like really real? It's a simple question, and yet it's the most complicated one we know how to ask. Because for all the technology we've built, all the formulas we've derived, all the elegant symmetries we've etched onto chalkboards and simulated in particle colliders, when we strip it all down to its bare essence, we're left with something strangely foggy, something that resists definition, that almost mocks our need for clarity. The deeper we go into the heart of quantum mechanics, the more the answers start to look like riddles. We're told that particles aren't truly particles until observed, that everything exists in states of probability. That time can stretch, bend, or even, according to some interpretations, reverse under the right conditions. That empty space isn't really empty, but bubbling with virtual particles. That entangled particles can affect each other instantaneously across vast distances as if space itself didn't matter. And yet, we wake up every morning. We brush our teeth, walk on solid ground, eat breakfast. The world feels real, tangible, stable. So what gives? Here's the thing. Quantum mechanics is the most successful theory in all of science. Full stop. It has predicted the outcomes of experiments with breathtaking accuracy. It gave us transistors, lasers, GPS, MRI machines, and quantum computers. It powers your phone, your TV, and the chip inside the device you're using right now. It's not fringe. It's not untested. It works. And yet, we still don't know why it works, or what it actually means. The equations are beautiful. The predictions are spot on. But the interpretation, what does this actually say about the nature of existence part, that's where things fall apart, or rather fragment, into a dozen different schools of thought, each offering a radically different picture of reality. Some physicists say, well, reality is fundamentally probabilistic. There is no single outcome, only likelihoods. Others say, no, the universe splits into infinite versions with every quantum event. All outcomes happen, somewhere. Others argue, no, it's just that we're missing hidden variables. Reality is deterministic. We just don't have all the pieces. Then you get the more mind-bending ideas. That reality isn't a thing that's out there, waiting to be discovered. That it's something that emerges when we look at it. When we ask a question of the universe, it chooses an answer, not before. That perhaps the entire concept of a thing existing independently of observation is just an illusion we evolved to help us survive. That's a tough pill to swallow, because it means that the foundation we build everything else on, our science, our technology, our very sense of being, might be floating on something more like fog than stone. Imagine looking at an object, a rock, say. It feels solid. It has weight, texture, temperature. But when you zoom in, down to the atomic level, that rock is almost entirely empty space. It's made of atoms, and those atoms are mostly just orbiting clouds of probability. Electrons don't have a defined location until measured. Their positions are just described by a wave function, a mathematical description of where they might be. Even the nucleus, dense as it is not truly a thing in the way we casually understand things. It's a set of bound particles that are themselves composed of quarks, which exist more like vibrations in invisible fields than like little marbles. So if the smallest building blocks of reality aren't really things, what are they? Maybe thingness is an illusion. Maybe reality, as we experience it, is a kind of user interface, a simplified model constructed by our brains to navigate a world far too complex and alien for us to grasp directly. Think of it like this. When you use a computer, you see icons, folders, trash cans, files. But those aren't what's there. Underneath is code, data, electricity, transistors flipping, ones and zeros. The interface isn't false, it's useful, but it hides the deeper, messier truth. Could reality be the same way? Could space, time, objects, and even causality be part of an interface evolution crafted for survival rather than truth? Are we the user, staring at the desktop, having no idea what's really running underneath the screen? There's a theory in physics that nothing we see is fundamental, not space, not time, no matter. Some theorists believe that reality arises from something even deeper, information, that everything is fundamentally data, and what we perceive as physical existence is a kind of output from quantum information being processed, not in a computer, but as part of the fundamental laws of the universe. And again, it's not some science fiction fantasy. These are serious conversations happening in serious institutions, with serious math backing them up, because the more we probe, the more we find that at the heart of it all, there aren't really things in the traditional sense. There are relationships, probabilities, fields, waves, code, the idea of an objective, observer-independent reality, that there is a universe out there just doing its thing, regardless of whether we're here or not, is becoming harder and harder to defend. Not because we don't want it to be true, but because the data just doesn't support it. So we're left with this strange tension. On one hand, we have a theory that works better than anything else we've ever come up with. On the other hand, we don't really know what it's telling us. It's like we've opened up the universe and found ghosts, not in the supernatural sense, but in the sense that nothing is as solid, as clear, or as graspable as we thought. We found a world made of maybes, of flickering probabilities, of particles that don't exist until they're seen, of events that can't be predicted, only described statistically, of actions at a distance, of energy fields that permeate the vacuum, of equations that tell us everything, except what the equations themselves mean. It's terrifying, sure, but it's also beautiful, because it means we live in a universe more mysterious than we ever imagined, a universe that humbles us, that refuses to be boxed in, that constantly defies our expectations, our assumptions, and our models. And maybe that's the point. Maybe we're not supposed to have all the answers. Maybe reality is a question, not a solution. A riddle that opens up into deeper riddles. A mirror that reflects not just what's out there, but who we are, what we believe, and how we see. So the next time someone asks you, "What's real?" you can smile and say, "We're still figuring that out." Because beneath everything we know, beneath the atoms and the equations and the experiments, there is a deeper truth, that knowing itself might be part of the story, that we, the observers, aren't standing outside of reality, trying to measure it like scientists peering through a window. We're inside it, we're made of it, entangled with it, and in a very real way, we might be shaping it just by being here. So what's real? We don't know. And maybe that's the most real thing we've ever learned. So, are atoms even real? It's a question that seems simple enough on the surface, but once you dive into the depths of quantum mechanics, it becomes far more complicated. The answer is, in a way, no, at least not in the way we thought. Not in the sense of little, neatly organized Lego bricks that can be stacked to build everything around us. Not like tiny solar systems with electrons spinning neatly around a stable nucleus. What we've learned from quantum mechanics is that atoms, the very building blocks of matter, are not solid, predictable, or constant. Instead, they exist in a state of probability, a cloud of potentiality that only takes on a definite form when we observe them. Are they real then? Well, they're real enough to build the universe. They make up everything. The stars, the planets, the air you breathe, the very cells in your body. They're real enough to create the experiences you have, the sensations you feel, the thoughts you think. But in a strange, paradoxical way, they aren't really real in the traditional sense, at least not until we look at them. Take a moment to think about that. Everything you touch, everything you see, everything you experience, it's made of atoms. But these atoms don't have a definitive, fixed position until they are observed. They don't exist in a clear state of being until someone, some conscious being, looks at them, measures them, or interacts with them in some way. What does that even mean? How can something that forms the very foundation of reality be so elusive, so uncertain? How can something that makes up all matter only come into existence when observed? The answer, it seems, lies in the fundamental strangeness of quantum mechanics. At the quantum level, particles don't behave like solid objects. Instead, they exist as a kind of blurry cloud of probabilities, a superposition of many possible states. Take an electron, for example. It's not in a single location. Instead, it exists in a spread-out region of possibilities. You could say, there's a certain probability it might be here, a certain probability it might be over there, and until you measure or observe it, it doesn't actually decide where it is. It's only when you look that the wave of possibilities collapses into a single, definitive position. Does that mean atoms are just a figment of our imagination? Of course not. They are real, in their own way. They're just not as real as we once thought. They don't have fixed permanent properties until we interact with them. They are a cloud of potentialities. Until we observe them, they don't have definite states. They exist in a kind of quantum limbo, neither fully here nor fully there until the act of observation pulls them into focus. Maybe that's the best way to understand atoms, not as solid, tangible objects, but as something closer to a dream. Imagine the way dreams feel. They're real in the moment. You experience them, feel them, remember them. But once you wake up, they slip away from your grasp, leaving behind only fleeting memories. Maybe that's what atoms are like. They are real enough to shape the universe, real enough to make up everything you see and touch. But like dreams, they exist just a little out of reach when you try to pin them down. And maybe, just maybe, reality itself is a kind of dream, a dream that the universe is having while we watch. Think about it for a moment. The solid, stable world that we experience day to day is built on particles that are not solid, not stable, and maybe not even real until we observe them. The ground beneath our feet, the air we breathe, the chair we sit in, all of it is made of atoms that exist in a state of quantum uncertainty, of cloud-like probability until we make contact with them. In the quantum world, things are not as fixed as they seem. The universe is not a place of rigid certainty. It's a place of possibility and potential, where everything is in a state of flux until we observe it. The act of looking, of interacting with the world, is what brings things into existence in the way we understand them. But this leads to an even bigger question. If atoms, and by extension, the universe itself, only become real when they are observed, then who or what is watching when no one is around? When no human being is looking at the stars or measuring the behavior of particles, what keeps the universe in place? Is it just an endless cycle of probabilities, each moment waiting for an observer to collapse it into reality? Or is there something deeper at play, something that keeps the universe intact, even when we aren't looking? Quantum mechanics doesn't give us answers, it gives us questions. And the more we learn, the more we realize how much we don't know. The world we experience, the physical reality we take for granted, is built on a foundation that is far more strange and mysterious than we ever imagined. Atoms, those fundamental building blocks of matter, are not what they seem. They don't behave like little particles bouncing around in predictable orbits. They don't even have definite properties until we observe them. In a sense, quantum mechanics flips our understanding of the universe on its head. We thought we lived in a world where objects had fixed properties, where things existed, whether we were there to see them or not. But quantum physics tells us something different. It suggests that reality is not a passive backdrop to our lives, but an active, participatory process, a process that depends on observation to take shape. And in doing so, it forces us to reconsider everything we thought we knew about the nature of reality, existence, and our place in the cosmos. So, are atoms real? Yes, but not in the way we thought. And maybe, just maybe, the universe itself is just waiting for someone to notice it, to look at it, to be aware of it. And when we do, it collapses into something we can see, touch, and understand, at least for a little while. Subscribe.